Okay, so I also want to look at finding out what's the derivative of e to the x, and this feature on our graphing calculator of finding dy dx is definitely something that the AP exam expects you to know how to do. And mainly because we're going to be able to evaluate very quickly and numerically what derivative values are. So again, going to your graphing calculator here. Pull up my online version of it here. There it is. So I went ahead and already typed in y equals e to the x, and I already have their table of values. So I can see that I can see that e to the first power is 2.718, and e squared is 7.38. 7.3891, and e cubed, e to the fourth, e to the fifth. So I think what I'll do, I'll just take a snapshot of that, so I know that it'll put it into my smartboard. So now I have them there. Oops, I wonder if I put it in the wrong smartboard. Let's see. Not responding. Dun, 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 dun. Oh, there it is. Well, I captured it, just put it in the wrong smartboard. So let me cut that out, and let's put it in the correct smartboard, which is here. All right, so there are those values, right? So you should fill out those values there. But more importantly, now let's look at our derivative values, right? So what is the derivative of e to the x when evaluated at 1? So we go back to our graph, and remember, you go second and calculate, and you pick your derivative, which is option 6. And I really wish it would prompt you what's happening. It really doesn't. So the first time you do this, you may think, wait, did I do it wrong? You hit 1 and then hit hit enter. Hit that for a second. Hit enter, and there it is. Dy dx at 1 equals 2.718. Well, that should look really familiar, right? Because we have a y value of 2.718. So right now, these two are identical. Okay? Coincidence? I guess we'll find out. So go back, second, calculate, derivative. It prompts now 2. So again, it doesn't prompt you, I should say, but you need to hit 2, hit enter, and we get 7.389. Does that look familiar? It sure does, right? Coincidence? No, it's not. And we can go through all of these, right? I mean, you could go through second, calculate, derivative of 3. So the derivative of e to the x when evaluated at 3 is 20.0855, and that should look familiar because that's exactly what e cubed is. So my point, or the point of this exercise, is that e to the x is a very, very unique function. And it's one of my favorites because it's its own derivative, right? E to the x's derivative is itself. And it's the only non-trivial function who is its own derivative. And I mean, not only is that kind of just a cool thing, but think about what does that represent? So that means the slope of any point in e to the x's graph is always equal to its y value, right? I mean, think about that. So if you just quickly, if you just quickly sketch out that graph, right, and you draw in your e to the x curve, we'll go that color, right? So, tricked you. That's not e to the x, that's natural log. Let's try that again. You draw in e to the x like this. So that means at any point in time, right, any point in time, let's say right there, whatever its y component is, as you look, whatever its y component is numerically equal to the slope of the tangent line, which again, to me, is just such a fascinating property of this function e to the x. Now, whether you're fascinated with it like me or not, it doesn't matter. You still have to know that it's its own derivative, and it's so simple that you'll never just see it by itself, but you will see it with chain rule. So it does not matter what the exponential power is. So I sometimes like to block that out, saying, okay, we can't really see what that is. It's e to something, right? It's e to some power. So the derivative means you're going to get that exact same thing back. So I'll go to black. There we go. So my f prime of x is e to the 4x, because that's what was there, right? Hidden. And then I do the chain rule times 4. Times, it was doing the last video too. That's crazy. I think it's, I feel like it's just the case of the Mondays. since that's the day of the week I'm recording on. Okay, so here it is. There's our derivative. But we'd probably put the coefficient of 4 in front and call it 4e to the 4x. It does not matter how complicated that exponent is. It has to stay, right? It does not change. You can't change the identity. You can't take the derivative too soon, too early. So now when I have, oh, there, hold on to that. Looking for, there it is. So now, again, kind of covering that up to do example 2, find that derivative. Okay, so when I do that derivative, it's going to be itself. You always get back the exponential expression. So f prime is equal to, and then what was that? Oh yeah, 3x squared. So we get e to the 3x squared power, and immediately we multiply by 6x because that's the chain rule. That's the derivative of this. So I probably put 6x e to the 3x squared, just, to keep that clean. Okay, next. Example 3, again, its derivative is itself. You do not change anything about the identity of what that exponent is. But then chain rule, it's a sneaky chain rule. The derivative of 1 minus x is just -1. So I probably would put that negative in front and make it look something like that. Negative e to the 1 minus x. Okay, and then e is not immune to product or quotient, so just be careful of the chain. So one derivative at a time. So the derivative of x squared is 2x. You leave e to the 6x alone, plus, and you leave x squared alone. The derivative of e to the 6x is itself. Chain rule times 6. So again, maybe cleaning that up and putting the coefficient in front. Plus 6x squared e to the 6x. Now, if you want to factor out a GCF, feel free to. I notice they both have e to the 6x. They both have an x and a 2 they could divide out, but this doesn't have to happen. Okay, now sine of e to the x. Remember, now the derivative of sine is cosine, and it's e to the x, can't change that identity, but then what's the derivative of e to the x is itself. So we get this multiplying by e to the x outside. So I might put it in front, e to the x times cosine of e to the x, but there is our function. Okay, so then here, natural log of e to the x. So remember, derivative of ln is 1 over that, so 1 over whatever's inside, and then the derivative of e to the x is itself. Well, e to the x cancels with e to the x, and so you get 1. And in hindsight, maybe you already noticed this, but natural log and e to the x are inverses. So this could have been simplified before to just f of x equals x. And then what's the derivative of x? 1. Right, so it shouldn't matter if you algebra first it or if you calculate first it. You should get the same answers. Okay, and it looks like we have one more example on this video of just quotient rule. So remember low d high. So I keep erasing by mistake by hitting the toggle button on my stylus. So low d high. So low x squared d high. It's e to the negative x times chain rule -1 minus high e to the negative x, no chain rule, right, because we're not doing its derivative, d low, 2x, all over low, so x squared squared. So let's see, I probably would put this negative in front, make it negative x squared e to the negative x, and I'd move this 2x with this negative here, minus 2x e to the negative x, all over x to the 4th. Now, nothing wrong with this answer, but it's not simplified technically because I can pull out an x out of the numerator and factor that out. So I would just get negative x e to the negative x, and then just minus 2 e to the negative x all over x cubed. Okay, so yeah, like I said, e to the x is an identity. It's its own derivative, which is a very, very unique property. And like I said, it's the only function other than like 0, because the derivative of 0 is 0. So it's like the only non-trivial function who's its own derivative. So really cool property. Okay, so hopefully again, you don't have to like know or prove anything. You just need to know the derivatives, right? Ln x is the reciprocal function. E to the x is its own derivative. Okay, very good.